Hello, my name's Steve Miller. I'm at the University of Florida in the Department of Mechanical and Aerospace Engineering, and I'm an assistant professor. Today I want to talk about a new course which I developed here at University of Florida on the Navier-Stokes equations with a historical perspective. In this talk, I want to talk about my motivation and desired outcome for the course, the objectives and overview of the course, show the course outline and what we created, the philosophy of the course, talk about what the students are given, some of the sampled historical figures and the material which is online, and maybe summarize the outcome of the effort, which took about 2 years of course development time in conjunction with discussions with mathematicians. That much research and analytical work, especially in the math community on Navier-Stokes equations, isn't completely in the math community and American Mathematical Society. And we want to convey these new developments and ideas to the fluid dynamics community, at least the greater one, and outside fields, and especially to engineering type classes. So the solution for this problem was to try and bridge the gap between mathematicians and the engineering community. Give this class, a special class, to the graduate students. This would indeed benefit and maybe give a practical understanding of the state-of-the-art of Navier-Stokes equations, solutions and analysis for CFD experimental work and analytical researchers. So the objectives are, for the students at least, out of the course, is to understand the history, the physical meaning, and contemporary challenges within the field of theoretical fluid dynamics and turbulence. And this is no by means an easy task because the subject takes years to learn. So here's the course description that was actually put out, and the course description actually follows the outline of the course. So let's just look at the outline of the course. The course starts with an introduction on the first day and gives the outline, defines the clay mathematics problem and what types of solutions we're interested in. We want practical solutions because the purpose of theory is prediction. Then we spend 3 days going to the historical development of the Navier-Stokes equations from very early Egypt through today. And we give a lot of history and details because, of course, it wasn't just derived by two people. There was many people, and they all stood on each other's shoulders to create this equation system, which we all basically devote our lives to studying. Then we'll do a mathematical review. We have a few days of mathematical review for the students and notation. There's lots of different notation and terms and important mathematical constructs, if you will, and background students need to know. And this is probably one of the biggest struggles in the course. And then we'll go through a in-depth derivation, Navier-Stokes, a greater in-depth derivation that's much usually presented in the graduate classes on fluid dynamics. And then we have a number of classes on the physical meaning. And this is where we look at the terms and tie them in with realistic flow fields so students can understand each term individually in the classical compressible Navier-Stokes equations. Then we look at a number of classical solutions. And by classical solutions, I don't mean those that necessarily are part of like what is taught for like laminar flow, like Koch flow or something, or Stokes' first or second problem. These are a little bit more complicated and represent sort of the state of the art today. Then we talk about stability, because of course stability is important for flows. This is like a hydrodynamic stability portion. We do stability analysis on the Navier-Stokes equations, both nonlinear and linear. Then we look at them as a dynamical systems. I wrote dynamical systems here. I apologize for that typo. And then we look at intro and just give an introduction to the ideas of uniqueness, regularity, and existence of the equations, because these are still open problems for incompressible Navier-Stokes, which is the clay mathematics problem. And then we also look at that for the compressible form of the equations. And we talk about ladder results, which are a classic theorem in Navier-Stokes. And we look at dissipation rates for turbulent flows and show that they're bounded, and I show how that CFD solutions can be checked, that if these dissipation rates are too high for certain initial conditions, then they have to be wrong because they can be proved mathematically to be bounded. We then look at blowup and Serrin's criteria, which is pretty typical. We make sure the solutions aren't blowing up, which can happen in compressible flows. Then we look at the capacitary approach, the Navier-Stokes integral equations. We look at differential integral forms. And then we look at the classic mild solutions. These aren't weak or strong, but called mild. There's Lebesgue, Sobolev spaces, Besov, Morrey, VMO, Koch, and Tataru theorems. And these are covered in maybe 6 or 7 classes. We then look at Leary's weak solution. That's a classic solution. And then we look at a 4 major parts of stochastic forms of Navier-Stokes, because I think this is very important for the students to understand in stochastic differential equations. And almost no graduate student had a background in that. So we have to do some mathematical review there. Many people say, what is this class and what isn't it? It's exactly an examination of the classical contemporary approaches for the solutions of Navier-Stokes equations, and we show how these methods are related to societal problems and how can we move to prediction methods. We want to focus on practical outcomes of analysis for practicing applied mathematicians and engineers. And it is a lot of material, and so students do have to work hard to kind of keep up. But I try to make it a balance between the difficulty of the subject preserving its essence with making it approachable for a graduate student with a background in PDE. This class is not derivation of trivial solutions like laminar flows with simplified boundary conditions. Those are not solutions that we're interested in this class. They've already been presented in previous classes. It's unfortunately not that easy to understand, and that's part of the difficulty of teaching it as a professor, and it's certainly not really a review, and students are encouraged to review on their own if they don't understand something, and we provide a lot of supplementary material to do that. Class handouts. Before every class, we give students handouts, and they're also posted on the website, and these are available to anybody anywhere in the world now, and we encourage the students to print them out or use a tablet and write in the blanks. So a lot of the equations, graphs, and some bullet points are blanks. And for example, if we had an equation y equals mx plus b, on the actual student handout, they would fill it in, and this encourages student interaction. I actually learned this from my advisor in grad school. Here are some examples of about the 92 historical figures in the class. Every time a historical figure name comes up in the class, we show some funny tidbits about them and where they're from and what they did whenever a named equation or term comes up with them. And so here's one on, of course, Jean-Baptiste Le Rond d'Alembert, one of my favorites. And I'll give you a second to maybe look over that on your own. One on Marie-Sophie Germain, and there are some women in the history of Navier-Stokes equations and the current analysis. I absolutely took the time to show that they're represented, and I'm really impressed by them. And of course, we have one on Claude Louis Marie Henry Navier and George Gabriel Stokes. You can read these by pausing the video if you want. And of course, there's much more in-depth information on these in the lecture notes available online. The students also had to write a term paper. They would choose their own topic, and it'd be about a 10-page paper at the end of the semester. They'd have to turn in a basic background review of the term paper and choose their own topic. Then would have to draft an abstract with a detailed outline. That's usually 3 pages. And into the term, they would turn in about a 10-page paper, and they could choose any topic as long as it's related to the Navier-Stokes equations and be more theoretical in nature. And of course, these are fun to read as a professor because I get to learn about the student's perspective and what they know and what they took away from the class. So all these material is available online, and you can use the QR code on the right to with your phone to go to the website, or you can go into the encrypted website, my website, saemiller.com/Navier-Stokes, and you can download a comprehensive set of the course material, and you'll get a full slide deck, my version, not the student version, with all the equations included of 1,768 slides. There's over 2,000 unique equations, including the Navier-Stokes equations, of course. There's 92 historical figure slides with fun facts, which were wonderful to research. And there's many little interspersed quotes by famous people. And this whole effort took 2 years to create and put together, so I hope you very much enjoy it. I'd like to conclude this talk by saying that we created a contemporary class that's available for anybody today, that's accessible to engineers with a background in partial differential equations and preferably some analysis. I hope it's valuable to community, and my future project will be to record these lectures free of charge for anybody who wants to view them and put them on YouTube and maybe Vimeo. Thank you very much for your time today. I'm Steve Miller.